guys. Okay, I'm feeling a lot better. My mind is back, as much as it ever was, I guess. Okay, I know I've explained to you guys about the problems with the lip lights. And what I wanted to do is give you, since I've become somewhat of an amateur expert at this problem, I wanted to explain to you guys in some detail exactly what's going on, exactly what the problem is. You guys see the videos and you go, oh wow, it looks fucking great, fantastic, you know, which it does, but there are problems, and I'll try to explain some of those problems here as we go along, and how I've addressed them and plan to address them. Okay, let me see here. Give me a second. Alright, problem one. This is the original circuit. Okay. What we have here is we have the voltage coming in, going through a regulator here. This regulator regulates the voltage down to 20 volts, which is supplied to the two ICs which aren't in there. I'm currently using this power supply, this 20 volts out, to run the new circuit. Anyhow, so you need that regulator, all the support componentry for that. You also need an additional regulator to run the audio amplifier IC, okay, to increase the line level input into the driver circuit, which then in turn creates a VU level output through the resistors out to the lip lights, of course, okay, and that just plugs in there. Sounds good in theory, and in theory it works-ish, but it doesn't. Okay, so let me set this up here and try to, let me see here, turn that down. Okay, so here we go. Here is the new and improved prototype circuit, and I'm going to put some music on here and try to explain and demonstrate what the problem is, or how the problem has been corrected, I should say. Okay, hopefully the camera is picking this up okay. Now, this LED, the end one, there's 19 on here. You may or may not be able to see this one flashing, but it is currently flashing. It's just at a fairly low level because that's the peak point. Now, let me see, I'll turn down my volume so I can think. Okay. If I take this, if I take and cover up about half of this display, I still get a usable output. Okay? I mean, I can cover up more than half of it, and you can see it's still going to the beat of the music. You can clearly see that even on the camera. Okay? The VU meter is not designed like that. The VU meter, and I'll show you, it just so happens this is running through a wire here into here. This is my 1980s, vintage 1980s Panasonic RXC 100 boombox. I had one of these in the 80s. The original got destroyed. I found this on eBay. Anyhow, these sold for $500 brand new when I bought my original. But here's a VU meter. Okay? Looks pretty cool, right? But if you cover up half of this, okay, wait till the music starts playing here normally. See right there what happens? You lose everything. You See, it's only during periods where there is a lull in the music that it actually displays. So basically, if I cover up this half, you can see the top half is flashing away, but of course the bottom half stays constantly lit. That's a problem with the lip lights, okay? Because that is an actual VU meter, and the circuit that I was designing from is designed as an actual VU meter, this created a problem for us. Our last 4 LEDs are on the very end of this lip light assembly, okay? So these could be flashing, but all the other ones would basically be full on, okay? So there was no real fluctuation, you know, throughout the display when there should have been, which is what is desired, okay? So, pause that. The problem is this, with a standard VU circuit, okay, with any VU circuit, the VU standard is that to go from a 0 input to a 0 on the VU meter, which is only about 3/4 scale, there's a 300 millisecond delay, okay? It takes 300 milliseconds for that rise and fall. That's a problem, because we lose all of our resolution. We would then, you know, if I covered up, you know, half of this display with the actual VU meter, these lights would stay solid on. They wouldn't flash to the beat of the music. The circuit that I've designed does away with all this. It treats the incoming signal as a purely a pure linear function of the voltage, okay? The output is directly proportional to the incoming voltage. The way I achieve this, and it's actually darn near impossible to see because they're so small, but on the underside I have a rail of small signal diodes which creates a voltage ladder. That voltage ladder, the incoming voltage is dropped, I believe 3/10 of a volt. It's either 3 or 6/10 for every diode it goes through. So as it goes through diode 1, it will drop the voltage 6/10 of a volt. So it creates a ladder effect, and each one of those diodes, once the voltage exceeds the diode's threshold, it turns the associated transistor on, and that continues throughout. Now, we don't have a delay, at least none that can be perceived by the human eye. We don't have a 300 millisecond delay as in a regular VU meter. What we have is we have a 10 nanosecond delay. That's the switching time of the transistors. So between 300 milliseconds and 10 nanoseconds is a huge improvement. Also, this circuit does not get hot. The resistors on this, just the first few get slightly warm, but the rest of it is just completely cold. Our transistors can handle a lot more current. What I'm going to be doing is I'm going to be putting a socket up here, putting in the lip lights, testing it that way. But bottom line is, this is a far superior circuit for our needs, okay? While the original circuit may have been accurate as far as a VU meter style, it was not correct to the Johnny 5 specification. That is, I don't know what they did, but all of the lights were constantly doing something. It was not a a non-linear function. It was linear, okay? And that's what I've replicated here. Circuit uses all discrete components, you know, resistors, transistors, and diodes. That's it. It's no more complicated than that. Any idiot with a digital voltmeter and a rudimentary knowledge of electronics can troubleshoot the circuit if there's a problem. And the circuit is inherently robust. I mean, there's nothing really to go wrong. If something stops working in here, trust me, you're going to see it. You're going to see a burnout component, or, you know, smoke's going to come flying out, or whatever. But anyhow, so that's the basic gist of things, why this has been such a problem. Although this component count may end up being higher than the old one, if you do notice, this is actually much larger than it needs to be. The resistors can be put vertically instead of horizontally on the board. All these components would be much closer together. But you can see here, I mean, I have the entire driver circuit minus the bootstrap circuit, which is a matter of about 3 transistors, some resistors, a few capacitors. Basically, it's a high gain amplifier to amplify, and not an audio amplifier. This would be a voltage amplifier. But anyhow, you can see here I'm using about, you know, actually less than half of the width of, about half of the width of this board. This board is the same size, and it's absolutely huge. You know, there's just, you know, there's no way to shrink this down to what this is going to, and this also includes LEDs. This one doesn't. So, as you can see, this circuit is just, for our needs, no, it doesn't function properly. This circuit here is far superior. We can go with larger transistors, which I may do, just in case. You know, for future, you know, in case we find incandescent bulbs, you know, the exact ones, and we want to be able to plug in one of these Liplight boards. We could plug it right into this driver circuit and it would operate identically. I mean, the circuit doesn't care whether it's LEDs or, you know, as to where this one over here does. This one here definitely gives a shit. Now you may be asking, well, why couldn't we put transistors on this one to solve the current problem? The problem was this. The ICs are inherently flawed in the fact that they have a very small current output. I had actually tried doing this before with transistors, same basic principle, but I used the drivers to actually turn on the transistors. The problem was the damn drivers was not allowing the transistors to fully turn off, so a lot of the LEDs would be dim. They would stay dim at 0 input. The other problem with this circuit is it requires an enormous amount of input voltage to get full-scale deflection. This circuit here requires, with 2 chips cascaded together, requires about 7.8 volts of input voltage from an audio amplifier, okay? This circuit here, I mean, you can do the math, but there's 19 LEDs, you know, 19 diodes, and each one only has, you know, it drops 0.6 of a volt off of the input voltage. So it's you know, hugely more efficient than the other system. So anyhow, I guess it is what it is. This is more better. This is not better. This is more better. Okay. I hope that explains it enough to you guys. It's a complicated problem that was exacerbated by the fact that I tried to go from an engineered product. This was something that needed to be dumbed down. And who better to dumb something down than a dummy like myself. So anyhow, I'm going to go, hopefully today, I'll wire in a new socket in here, get the lip lights in there, run some tests on there, and get some actual data on the actual lip lights. But this is the basic setup here, and I just wanted to let you guys see and know what was going on. Alright, let me see here. La 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 la. Alright, okay, bye for now.